everyone. My name is Marco Pavone, and today I will be discussing my work on interaction-aware decision-making. Before starting, I would like to thank the organizers of this workshop. My lab, the Autonomous Systems Lab, focuses on the design of planning and decision-making algorithms for autonomous robots. That is, on the design of techniques that allow robots to make decisions on their own. A key focus of our research is on designing techniques that allows robots to interact with humans in a safe and efficient manner. For example, let's consider the case of autonomous driving, which is a typical task that requires complex interactions with other humans. In this example, which entails vehicles merging on the road, we see that the overall goal of everyone on the road is clear to everyone, but the outcome of the interaction is very unclear and it really depends on a complex and often aggressive negotiation. More in general, merging into traffic and driving entails an exercise in negotiation, and robots should be able to perform such negotiations for safe and efficient driving. Alternatively, as I like to say, robots should be able to perform proactive decision-making. That is, they should be able to proactively interact with other agents in order to infer their intents, while concurrently exploiting this information to take actions that account for agent responses. My approach to this problem is model-based, whereby a probabilistic understanding of the interaction dynamics is used as a basis for policy construction. This is different from model-free approaches, whereby human actions and responses and relative likelihoods are only implicitly encoded into a policy that is learned directly from data. And the rationale for this decoupling between human intent prediction and decision-making is to achieve a level of transparency that is difficult to achieve in a model-free approach. Now, in a model-based approach, the first task is the task of intent prediction, or more specifically of trajectory forecasting. And this will be the focus of the first part of this talk. My work in the context of trajectory forecasting is motivated by 5 key considerations. First of all, from the perspective of decision-making, we are interested in predicting human behaviors conditional on, that is, in response to possible candidate robot actions. Second, we are targeting action and reaction responses at a time scale in the order of about 1 second. This is different from traditional high-level decision-making that reasons in terms of multi-second macro actions. And this is also different from low-level collision avoidance control that typically has to run at a level of milliseconds. Third, at this time scale, human behavior is typically multimodal. What I mean by that is, let's consider, for example, the case of lane changing. So here we have a robotic vehicle depicted in green that wants to change lane. So it's a traffic weaving scenario. So in order to capture the natural interaction, what the robots want to understand is whether, if the robot were to accelerate, what would be the possible responses of the human-driven vehicle? Well, in this case, we will see that most likely the human vehicle would accelerate, but the human vehicle might display an aggressive behavior and it might actually accelerate. And this corresponds to 2 different modes. That's what I refer to as multimodal behavior. Or alternatively, in this case, if the robot were to decelerate, then again, the human might display 2 different modes, the first one corresponding to acceleration and the second one is corresponding to deceleration. The key point is that at this time scale, human behavior is typically multimodal, and the trajectory forecasting should account for such a multimodality. For consideration, we want to consider an intent prediction module that accounts for history. This is in order to uncover latent behaviors such as alertness or aggressiveness. And finally, we would like to have an intent prediction module that is as interpretable as possible in order to ease debugging and in order to increase the level of confidence in such a technology. Now, a typical approach to intent prediction, which I refer to as ontological or theory of mind, postulates some structure on the human decision-making process. For example, in terms of a cost function that a human is trying to optimize. This is the typical approach, for example, of inverse reinforcement learning. Now, a human in general is neither cooperative nor adversarial. As such, a fuzziness of behavior is difficult to reconcile with a theory of mind approach that ultimately is rooted in game theory. So in my lab, in the past couple of years, we have been investigating phenomenological approaches. The idea of a phenomenological approach is to directly learn the probabilistic structure of an interaction without reasoning about the underlying motivations. That is, without reasoning on how a human makes his or her own decisions. To do that, we have leveraged techniques from generative modeling. Now, there's been a lot of exciting work recently on generative models. What our work differs from the norm is that we not only want to predict the future based on past observation, but also we want to reason contingent on what an autonomous system might do in the future. Specifically, we want to learn a probability distribution P that allow us to predict the future action of a human. Subscript H stands for human. We assume that we are at time t, so t plus 1 is the next time step. And we want to learn such a probability distribution conditional on the history of the interaction. X denotes the relative states, for example, relative positions or relative velocities. And U denotes the past controls by the human or by the robot. And critically, we also condition on a candidate future robot action. Conditioning on the past allow us to uncover latent behavior such as alertness or aggressivity. And the conditioning on the future allows us to capture the interactive aspects of an interaction. Practically, in order to learn such a distribution, we use a conditional variational autoencoder model. The way we use this model is as follows. Let's consider again the previous traffic weaving scenario, where we have a robotic vehicle that is trying to exchange lane with a human-driven vehicle. In this plot, on the x-axis, I'm showing time, and on the y-axis, I'm showing longitudinal acceleration. A solid line means something that has happened in the past, where dashed means the future. Specifically here, we're seeing that in the past half a second or so, the longitudinal acceleration of the robot, depicted in blue, and the longitudinal acceleration of the human, depicted in red, is 0, which means that both the robot and the human-driven vehicle were going at constant speed. Now, the way that we use this model is as follows. If the robot were to enact as a candidate action sequence an acceleration, then a coasting profile, and then a deceleration, what would be the reaction from the human? And in order to answer this question, we sample the generative model that we have learned from data. So in this case, you see that a bunch of samples will predict that the human would decelerate, while a few samples, so a few predicted trajectories, would imply that the human, perhaps because the human is aggressive in this case, would accelerate. And here also we see how these models can capture the multimodality aspect that I was referring before. So how do we use such a prediction model for the purposes of control and decision-making? In actuality, considering the case of traffic weaving, we consider about 4,000 action sequences, that is motion primitives. For example, motion primitives might say that we go straight, or we make a sharp turn, and so on and so forth. For each motion primitive, we generate a distribution of possible responses by sampling from the generative model that we have learned, which again is based on a conditional variational autoencoder. In actuality, we sample about 100,000 human responses per computation cycle. And by leveraging GPUs, of course, this sampling procedure is highly parallelizable, we can compute decisions at about 3-4 hertz, which from the perspective of a high-level decision-making is good enough. In particular, for each motion primitive, we sample a bunch of possible human responses. We score each motion primitive according to some aggregate cost function that combines task fulfillment with a penalty for collision avoidance and a few additional terms. And then we record the motion primitive that scores the best. We drive the first chunk of it, and then we replan in a receding horizon fashion. Now, critically, in order to score a motion primitive, we consider an expectation operator. So basically, we look at the average performance. An interesting question is, since we have distributional information about human responses, would be how do we account for risk? That is, in order to score a motion primitive, how do we replace average performance with some risk measure that accounts for what might happen in the tail of the distribution? For example, to account for particularly bad behavior that a human might exhibit. Now, the topic of how to account for risk in a decision-making context is a fascinating one. And I don't have time to go into the details in this presentation, but if you're interested, I will refer you to a paper that I co-authored with a former postdoc in my lab, Ani Majumdar, now a professor at Princeton, which it can be viewed as a sort of a position paper on how we think about modeling risk from a robotics perspective. Now I'm going to show some human-in-the-loop simulation to showcase how this control pipeline works. The simulations are human-in-the-loop in that there is a human that is driving the blue vehicle. So this is the human-driven vehicle that was also depicted in the previous figure. And then the robotic vehicle, the white vehicle, drives by using the prediction, the intent prediction algorithms and the decision-making algorithms that I have just explained. And data is collected by using the same driving simulator by having two humans driving side by side on a variety of interactive scenarios, such as traffic weaving, as we discussed, but also negotiating intersections and so on and so forth. So here on the left-hand side, we see predictions in terms of longitudinal velocity and longitudinal acceleration for specific motion primitives. As you see, you have a bunch of possible trajectories corresponding to the many possible ways that a human might react to a candidate robot action. And in the simulation, you saw there were some interesting behaviors that emerged, like, for example, the white vehicle, the robot vehicle, nudging a little bit on the other lane in order to probing the intent of the human. So the behavior is quite natural and quite efficient and safe. This is great until a disaster happens. So here I'm showing a case whereby the human, the blue vehicle, behaves in a way that defies the prediction of the intent prediction module and crashes into the robotic vehicle. So this is bad. But I would argue that in some ways is unavoidable for three main reasons. First of all, the intent prediction module that I have just presented is a probabilistic prediction approach. And probabilistic predictions sometimes might get it wrong. This is the same for humans. Of course, we make predictions about other agents around us, Those predictions are probabilistic, and sometimes we may get it wrong. Second, and another critical reason why sometimes we might have very undesirable behaviors is that at this level of decision making, collision avoidance is typically included as a penalty function in an aggregate cost function that includes many other terms. And this might cause conflicting objectives. And finally, as I said before, we can plan at about 3-4 hertz with this methodology, which ultimately is too slow to ensure safety. So the key question is, how do we integrate a probabilistic decision-making module that is targeting efficiency with a lower level control module that tries to promote safety in a way that does not unduly impact performance? So we've done quite a bit of work in order to address this question. And the key idea is to use techniques from backward reachability in order to reason in terms of interaction at the lower level of the control hierarchy. Specifically, the way that our full decision-making control stack works is as follows. The interaction planner, so the decision-making modules that produces predictions according to our conditional variation autoencoder prediction module, produces a desired trajectory. In parallel, we have a reachability cache that is computed offline that captures the notion of unsafe sets. That is, sets of relative states that might lead to collisions despite our best effort. For example, in this picture here, the red vehicle is the robotic vehicle, and this set would represent the unsafe set. We don't want the other vehicles to enter this set because otherwise, no matter what we do, there might be an action for the human-driven vehicle that might lead to a collision. And then we integrate the reachability cache that reasons about interaction in a worst-case sense with the probabilistic interaction planner that reasons about interaction in a probabilistic sense through a trajectory tracking module that produces actions that minimally deviate from the desired trajectory from the interaction planner in order to comply with the constraints that stem from the reachability cache. In other words, as soon as another vehicle enters the unsafe set, the tracking controller corrects the trajectory in order to take the robotic vehicle outside of the unsafe set. The trajectory controller is based on model predictive control and runs at about 100 hertz. And we have tested the full decision-making control stack on a full driver-wire self-driving cars, showing that actually we can seamlessly integrate high-level probabilistic decision-making aim at promoting efficiency with a low-level control rooted in reachability theory aim at ensuring safety. Now, in the past year, we have been extending these methodologies along 3 main lines. First of all, so far, I've been talking about pairwise interactions, that is, interactions between a robotic vehicle and a human-driven vehicle. We have been extending the models to account for multiple agents, possibly belonging to different semantic classes, such as pedestrians, other vehicles, trucks, and so on and so forth. A second direction is how do we produce representations for intent prediction that are better tailored to downstream control applications. And finally, we've been working on how to better integrate intent prediction with perception in order to account, for example, for the uncertainty that stems from the perception module. Let me start with our work on generalizing our CVAE-based prediction approach to multiple agents. Specifically, we have been working on enlarging our model in order to condition predictions on a vast set of heterogeneous data. In particular, now we can produce predictions for human intent that account for dynamical information, that is, account for the fact that the dynamics of a pedestrians, of course, are very different from the dynamics of a car. And also all the way to accounting for map information as encoded by a map encoder, capturing, for example, information such as a crosswalk or road boundaries. The overall methodology we refer to as a Trajectron++. All the code is available on our GitHub. And it turns out that actually incorporating heterogeneous data in terms of dynamical information and map information is extremely important for intent prediction. And perhaps surprisingly is oftentimes overlooked by other intent prediction work. Specifically to make this point clear, I'm showing here at the bottom experiments on using the new scene datasets in order to predict future trajectories of a number of agents on the road. For example, vehicles, pedestrians, and so on and so forth. In the left panel, I show the predictions based on our base model. That is a model that only accounts for the history of interaction in terms of relative states and relative control actions, but does not account for dynamical information, nor does it account for map information, for example, capturing the geometry of the scene. So here we see, in the context of predicting the future trajectory of this red car, that our prediction actually undershoots the ground truth depicted by the white car. In the center panel, we now consider the case where we augment the base model with what I was referring to before, the conditioning on dynamical information. It is conditioning on the fact that actually the red vehicle is a car, which is, in our case model, as a dynamically extended Dubitz model. So here we see that in this case, the intent prediction produces as outputs two different modes. One that predicts the red vehicle making a right turn, and the other mode that predicts the vehicle going straight. Finally, in the right panel, we augmented the base model by accounting both for dynamical information as well for map prediction. Now we see that the model further corrects the prediction, which now lies almost perfectly on the ground truth. Second aspect, as I mentioned before, we're working on is how do we find the representations for intent predictions that are more conducive to decision making. More specifically, typically the output of an intent prediction model is represented by individual trajectories for the agents in the scene. And this is a very natural prediction output. But unfortunately, it's quite difficult to work with from the perspective of decision making. As we saw before, in order to compute actions by considering a distribution of possible future individual trajectories from the other agents, we had to perform a fairly brute force approach, whereby for each motion primitive, we produce a bunch of samples, we score them according to an aggregate cost function. It's okay, but it's very brute force. So the question here is, how do we reason about prediction representation that are more cognizant of the downstream control applications? As far as I'm concerned, I'm interested in trajectory forecasting insofar it improves decision-making for the autonomous robot. Having said that, we have been considering a system theoretic representation of future intent by modeling future trajectories through as a linear time varying system. That is, the output of the trajectory forecasting module is a set of matrices AT, VT, and CT, which model the interactive structure of a scene. Specifically, the trajectory forecasting model learns the off-diagonal elements of the system matrices, which capture agent-agent interactions, as well as the effect of one agent on the Ego robot. So we learn all the green blocks. We do not learn the diagonal blocks because these diagonal blocks represent the agent dynamics which we assume are known. For example, in the case of the Ego vehicle, will be the dynamics of a car. Just to be more specific, in this example, here is a scene with 3 agents. We have the robotic vehicle and 1 human-operated vehicle and 1 pedestrian. So this translates into a system matrix that is partitioned according to a 3x3 block. And we also account for, since we're interested in control, we also model the robot action that allows the robot to reason about its future impact on the of its control actions on the other agents. Now, the key point here is that if we learn this representation of future trajectories, then this representation is much more amenable to control because it can be readily embedded in a variety of control pipelines, such as a stochastic MPC. This is work that is in preparation, and we plan to publish in a month or so. Finally, and complementary to what I have discussed so far, is how do we integrate more tightly trajectory forecasting with perception. For example, and we're looking at this problem through 2 main directions. The first direction entails reasoning explicitly about the uncertainty that stems from the perception model. For example, here we see that objects that are far away are much more difficult to detect and classify. And in this image, you can see that each object comes with a classification score. So we're working on how to account for such a classification score in the trajectory forecasting process. Or in equivalent terms, how we are working on how to propagate uncertainty from the perception model all the way to the trajectory forecasting model. Related to this, perception, of course, is also quite noisy. For example, in this video, you see how the yellow vehicle has a classification that switches at a very high frequency between being a truck and being a car. So we're working on techniques to make trajectory forecasting robust to noise that stems from perception, in particular in terms of frequent class switches. To sum up, I have presented our work on generative models for trajectory forecasting. And I will claim that in general, generative models, that is phenomenological models, are becoming the state-of-the-art tool for trajectory prediction. And then we have a survey paper on generative models for trajectory prediction that is coming out soon. So if you're interested, check out my webpage in a month or so. But as I mentioned, integrating generative models in the autonomy stack, that is integrating generative models with the downstream decision-making logic and with the upstream perception module is in general quite challenging. So right now we are working primarily on how to find principled ways to integrate generative models with the other components of the autonomy stack. In particular, in terms of reasoning about prediction representation that are cognizant of downstream control application through a system theoretic formalism. And 2, methods to tightly integrate perception and trajectory prediction in order to account for the uncertainty and noise that comes from perception. All of our code is available on my lab GitHub, and I would like to thank my collaborators. In particular, most of this work has been done by Karen, Boris, and my former student Ed, who is now at Waymo. If you have any questions, feel free to send me an email. And here you also have the rest of my contacts. Thank you very much for your attention, and I hope to see you all soon in person at some other venue. Thank you.